Alrighty, I think we're back. I'm going to keep an eye on the stream again just to make sure that everything's hunky-dory. It looks like OBS doesn't like playing well with Unreal 4, probably because I'm really taxing the video card on my machine. But if it starts to get wonky again, don't worry. I'll try and get it fixed, and if nothing else, we can just move back to Marmoset, which seems to play a little bit better with the stream. Um, Regardless, let's get back to what we were talking about before. So here you can see that we have a very, very basic shader. All it has is a 0 value for metallic and a 0 value for roughness. In terms of what you could expect from a specular shader, this is the equivalent of saying that the specular value is 0.04 and the gloss is 100%. So I can change this. I can say I have a separate value for gloss or roughness. I can plug this in, change this to say 0.5, and then in a second it's going to update this little preview, and you're going to see that it looks a lot less glossy. Well, and it looks like, yeah, Unreal is not playing very well with the stream here. It's taxing it a little bit. So what we'll do is we'll jump out of Unreal. It's either a compatibility problem with OBS or something else, but we'll close that for now. Go back to Marmoset and start talking about the different types of shaders you're going to run into, and the different ways that each of them affects the final render. So let's close all that stuff. Make sure that it's all dead. Alrighty. And that. Okay. So it looks like the stream needs to catch up. Sorry about this, folks. I was not anticipating that Unreal would be such a drain on the ability to stream stuff, but hopefully it's not a problem in the future. And oh, and the stream's still being funky. I'm really sorry for this. Okay, looks like, yeah, it looks like we're back in business now. The stream seems to be alive again. So yeah, let's get back to it. So, different types of shaders. Now we've talked about this a little bit before. Let's see here. We've talked about different types of shaders a little bit before. But let's talk about how different types of shaders actually affect certain aspects of the render. So we'll turn these lights back on, and let's just get this looking as fancy pants as possible. There we go. Everything's visible. All right. So as I mentioned before, in this scene we have several different types of shaders. We have the shader that I mentioned, which has his clothes in it, which has, you know, normal gloss, specular, along with other things like a little bit of a Fresnel term in the diffuse for this kind of like fuzzy look around the edges. However, in addition to that fairly basic shader, which is something that we've seen a lot of before, we have some other stuff going on. For example, we have, for his eyes, we have a completely emissive material that has a texture plugged in, which makes it so his eyes glow. Well, that's cool. Additionally, we have the shader for all these special effects, which does a lot of different things, but really is just like the additive transparency that I have on the eyes for that rock and roll dude that I was showing before. What else do we have in here? We have, looks like we have a shader just for his head, which is, it has no reflections, it has no occlusion nor normal maps on it. It's just a flat color, and it's set to the unlit mode, which basically shows a flat color, or rather the flat color of the albedo without being affected by any light. If I hide this, you can see that it's just a black silhouette for his head because it's completely unlit. It doesn't receive any lighting information, and all it does is look completely black and cast some shadows. Now, once again, for this frame around the base, it's a fairly simple shader, and it just has just some. Let's see here. Let me make sure that I've got it right here. Yeah, it just has some streaky stuff in the gloss and such. Now, these are all things that we've seen before. These are different ways of basically just shading the same type of thing. However, let's take a look at something that we haven't looked at very much. This is something that we briefly touched on for the eyes in the other character, specifically the irises and pupils. So let's hide everything that I don't want to talk about right now. Oops. Hide that. And we can hide that, and that, and that. Oops. And that's a light that's visible. We don't need that right now. So for this floor, I wanted to get a lot of texture in it, a lot of depth, but I also didn't want to have an exceedingly high polygon count. Now, unfortunately, if you don't want to have a high polygon count, but you also want depth that looks like, you know, it looks like the floor is made of modeled out bricks, you're kind of out of luck if you're not, if you don't have access to more advanced shaders. However, we're lucky in that we do have access to advanced shaders, and something that we have in this shader right here, and I can turn on the wireframe just to emphasize what's going on here. Now here is the model for this floor, and you can see that it's actually just completely flat. It's just a bunch of polygons going straight to the center and meeting there. And if we look at it from an angle, it works a little bit better with the wireframe turned off. If we look at it from an angle, we start to see that it appears to have more depth than that. There are parts, like right here, where you can see that the areas between the rocks, where the grout and the moss are actually pushed in. Now, this is something that you can get with displacement maps by subdividing your mesh and having the height of the mesh controlled by a grayscale value from black to white, or vice versa, with the various levels in between contributing to the actual physical height of what you see. However, what we're seeing right here is something different. This is parallax mapping. So parallax mapping, similarly to displacement mapping, affects how high or low things appear to be in the texture. The difference, however, is that the actual surface stays the same height no matter what. You can look at it from a glancing angle and you begin to see that it is just completely flat. The only difference is that from glancing angles, it looks like it has depth going down into the model, even though there's nothing there. So how does this work? It's actually fairly simple. The way that this works is that the dark values, just like with displacement mapping, appear to be pushed in, and what it's doing is it's taking that value and actually transforming the UVs of the texture so that they appear to be in a different spot relative to the plane of the camera, the plane of the screen, where you're looking at it from. So if I turn off this height map, you can see that, oh my goodness, let's reset the camera there. If we look at this from any angle without the parallax mapping turned on, we can see that it's completely flat. However, if we turn it on, what it's doing is it is pushing the texture across the screen or across the object's UVs relative to the angle of the camera, so that it appears there's depth. This is something that works from any angle because it's transforming relative to what you see. It's transforming relative to the plane of the camera. So this is parallax mapping. It's called parallax mapping because parallax is, it's like when you're looking out the window in a car, driving down the highway, and things that are closer to you seem to be going by much faster than the things that are far away from you, even though you're traveling at a constant speed. So what it's doing is it's taking the things that are closer and changing how much of them you can see in the UVs according to the depth map. So parallax mapping can be used in a lot of different ways, but one of the problems with parallax mapping is that it can't actually shadow itself. It can't actually change the lighting information of what's hitting it because there's no way that it can change the normal of the surface. So in this case, what you'll need to do is use a normal map along with the parallax to get something that is more believably lit. So if I turn down the depth, you can see that even with the normal map, it behaves as you would expect. It looks like it has a bit of depth. With the parallax map, it has even more depth. However, without the normal map, none of the lighting changes in the specular term because it simply cannot mathematically affect the specular term, because the way that the specular reflects off is based on the normal of the polygon that's reflecting off of. Now, you can set up very complex shaders that are pretty heavy that do actually change the the specular behavior based on parallax map. However, they're usually a lot more pain than they're worth. And they involve a lot of math and a lot of things like vector transformations and a lot of the things that you would see in something like a Photoshop normal map filter. They use a lot of the same math as that. And in the end, they just don't end up looking as good as simply having a normal map applied. So this is something that is entirely shader based, which is an example of weird ways that shaders can affect the way that your model shades. Let's talk about some other ways that you can change the shading of your model or the behavior of your model's surface with a shader. So in this case, let's use some displacement. Now, displacement and parallax are very similar, as I mentioned before. The dark values in the height map, the parallax map, this guy right here, the dark values correspond to areas that are deeper in, and the white values, the lighter values, correspond to areas that are higher up. However, the difference between a displacement map and a parallax map is that a displacement map will actually affect the geometry. It'll affect where the polygons actually go in three-dimensional space. So let's do that right now. We'll change this to height. It's going to take a second for it to apply here because once again I'm running OBS and have a lot of high-res textures loaded. Let me just get the location for this texture real quick so I can put it in there. One moment. So we'll just plug the height into there. Now, there's some really janky stuff going on here. Don't worry about it too much. We'll get that fixed in just a second. So let's turn this down a bunch. Let's turn off the height map in parallax, and let's take a look at this. And let's turn on wireframes just so that we can have a good reference for what's going on. So, shaders not only affect the actual physical shading of the model, but they can also, because of fairly advanced modern rendering techniques, they can affect the polygon position as well. You can do things like animate a texture that scrolls across a model, and what that does is what it can do is it can make it do things like wave in the wind like a flag. You could have a model that's a simple little rectangle with a bunch of subdivisions in it, and you could pass a scrolling texture across it that has some white values and black values that make it change its position kind of like a flag. Now, in the case of what we're doing right now, we just want to push the polygons up or down depending upon the value of this displacement map. So the dark values are going to go down, hopefully, and the white values are going to go up. And that's exactly what happens. You'll notice that in the areas along the edge where there's a lot of geometry, where there are dark values, it's being pushed in, and the light values, or the tops of the bricks, are being pushed out. Well, cool. That's great. That's awesome. However, in most cases, with displacement, a game res model, even one that's fairly high res, like you might see in, say, Uncharted 4, they're not going to have enough polygon density to actually get good results, kind of like you see in the middle of this model right here. So what can we do about that? Well, we don't want to import a high poly model into the engine. We don't want to make something that's so high res that the computer can't process it in real time. So there has to be another option. Well, luckily for us, because we use modern shaders, there actually is an option, and that is that we can subdivide the model in real time. Now, there are different methods for subdividing models in real time, just like there are different methods for subdividing models in 3D packages that let you use things like subdivision surfaces. The most common ways to get this sort of subdivision are through different algorithms that either take a triangle and just split it up, but don't change how it's curved at all, or there are ones that do a fair approximation of, say, Catmull-Clark subdivision, like you would see in Maya or 3D Studio Max or Modo, but they do have some limitations simply because of the fact that they're entirely within a shader and they only work on triangles. So let's try the two that are available in Marmoset just to show how they affect certain things and show what you can achieve in real time as long as you stay within the budgets of whatever it is you're working on. Okay. So you can see that once I turned on subdivision, it made basically this entire thing go white, and that's because I have wireframes turned on. However, if we zoom in really close, what we can see is a whole mess of weird, jaggy triangles and lines and stuff that are based on the geometry that I had before, but you can see that it's all been subdivided. So each triangle has been subdivided several times, and it's probably a little bit more visible here on the edges. Let's just turn this down. So if you look at these polygons around the edges, you can see how the subdivision or tessellation affects them. And it will affect things more or less depending upon where they are on the mesh and how big they are in reference to other triangles, but yeah. So you can see that as I crank this slider up, it gets more dense, and going back down, it goes back to something like you would expect. So that's sort of, the standard behavior that you would expect for subdivision anyway, is it just cuts up your polygons. But as I mentioned before, there are different methods of doing it, one of which just makes flat triangles, and some that make curved surfaces. So let's try that again without the displacement map turned on, and we can see what happens as well. So similar, just without the displacement. Now, if you look at the edge right here, where these triangles are being pushed down right at the edge, you'll see that when I use this flat tessellation, it doesn't actually change much of the shape. Really, all it changes is how many triangles. Well, I mean, it does change the shape a little bit because it's being a little janky since it's all very long stretch triangles, but in flatter areas like over here and over here, it doesn't change much. However, if we switch this to the PN triangles setting, it will start to change the shape a lot more, simply because it's trying to average things out. So we can change let's change the tessellation, and let's look at this edge right here. If we turn the smoothing down and up, let's see here. Let's try. Well, it often works best on gentle curves. Let's try it over here and see if we can't get something a little better. Here we go. Well, or perhaps not. This is probably not the best example for this specific type of shader, but that's okay. If you try it on something like a character with chunky ears, you will see that the ears smooth out. That's one area that's nice to use this type of subdivision. Now, as I mentioned before, displacement maps and tessellation work a lot better than parallax mapping to achieve a look of depth because they actually change the position of triangles. They actually change the position of polygons of your model. So you can see that as I change the scale here, along that far edge over there, you can see that the silhouette of the model is changed. It's actually pushing the polygons around. However, very similarly to using parallax mapping, in most cases, using a displacement map will not change the behavior of the specular because, once again, the calculation necessary to determine what the new normal is of all these new polygons when using displacement is a little bit heavy when you're just talking about shaders. However, you will notice something very different from when we were talking about parallax mapping, and that is that you can see some cast shadows here. So what's that all about? Well, this is another shader-based question, but it takes the form of how lights behave in 3D and how lights cast shadows in 3D. Let's go back to Photoshop and just draw a real quick example of how this works. Let's just let's delete all this, make it white, and let's make this smaller. So if you have a light in 3D, let's say it's up here, and it's casting light down in that direction, certainly there's going to be the calculation involved in determining which way the normal is facing so that you know how to shade it, so you can apply that gradient from white to black. However, this is not going to give you any cast shadows because all it's doing is looking at the surface of the model and saying which part of the model should be light and which should be dark. It's not actually going to tell you which parts should be actually casting shadows. So if you have a cube, all that little mathematical equation is going to do is tell you that this surface over here should be dark since it's facing away from the light. However, because we use rendering that goes in multiple different passes, recall that I mentioned the albedo pass and the specular pass. Each one is sort of rendered as a different layer and then composited together. Since we use that type of rendering, one thing that we can use is a depth pass. Let me just get a quick depth map for you. Just show it right in here. So these are probably familiar to most people who've seen, say, those Magic Eye books, where it has a bunch of repeating patterns that, if you look at it just the right way, you can see interesting shapes and silhouettes in. Now, this is because you can use a depth map. Each one of these is a depth map of a scene, and basically what they do is they show a value from black to white or white to black that corresponds to how far away something is in a given scene. Now, if you have a depth map, you can actually look at what is close to you, what is far away from you, and what angle you're at in reference to all that stuff, and then project this map onto the scene so that if you have that cube, when you're looking from the camera, you can see that this corner is closer, this corner is farther away, and this corner is completely blocked off by the rest of the cube. Therefore, if you project that map onto the scene, what you'll get is blank areas. This area right here will not be in the depth map, and it will not get any brighter when it's closer to the light. Therefore, you can actually use that to say anything that this light can't see, such as something along behind here. Doot, 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 doot. Anything in this area, it just won't show any light in there. And that's what it's doing right here. Let me unlink these lights from the camera since they're following it right now. So we can see that this key light, when I turn the shadows on and off, it's doing exactly what I just described. It's looking at the depth from the light to between here, and it's saying if there's no, if I can't see anything behind there, I'm just going to draw it as dark. So that is something that you can get when you use displacement mapping with tessellation, because it's actually changing the depth in the scene that it can see, even if it's not changing the shading. So how can you get around this sort of weird flat specular effect? Well, it's the same deal as using a normal map with parallax. You just simply load a normal map onto it, and it will understand the lighting that it needs to apply based on the normal map that you have. Okay, cool. So those are some fairly interesting, if non-standard, effects that we can get with shaders. However, they're not always very useful for characters. So what are some useful types of shaders for characters? Well, obviously, since this body has diffuse and specular and normal on it, those are going to be useful. However, as we've seen before, there are other types of shaders. For example, flat shaded ones. Flat shaded shaders don't actually receive any of the same lighting that standard shaders were, as I mentioned with the head, but they can be used in different ways. For example, if I have a flat shaded shader that has bright white in it, and I have some bloom in my scene, what that's going to do is it's going to affect the bloom because it's not receiving any shading whatsoever, so it's just rendering as that flat color. It's exactly the same as using an emissive texture, except that when you use emissive, you can combine it with things like gloss and specular, and other types of shading. So flat shading is the same as using an emissive, except the emissive is only rendered as a part of the larger shader, whereas a flat shaded one is just simply the single flat pass. However, this is only really good for items that either are completely black, like you see here, or that glow. So let's talk about skin shading. Let's really dive into skin shading and take a look at how skin shading sort of works, especially in current gen, and take a look at some of the different options for skin shading, along with diving into why skin can appear weird if you use the wrong colors. So let's turn off global illumination just to speed things up a little. Let's hide everything but his head and eyes. And then we can start talking about skin. Let's just hide all these. All right. Now we do want to see the eyes. There we go. Okay, so the skin shading that's present in Marmoset Toolbag as well as Unreal 4, they're very similar, and they're very close to a lot of skin shaders that you'll see in a lot of different modern rendering setups. The skin shaders that you see in things like Frostbite, proprietary engines like the one we use at Insomniac, there's all kinds of stuff going on behind the scenes, but a lot of them is based on the same work that was done by people at NVIDIA and other companies working closely together to achieve something that is physically plausible or behaves similarly to how you would expect an actual physical sample of skin to behave. So what do I mean by this? Well, there's a lot that goes into it, but let's start with how light scatters through the shader. Now, it's pretty obvious to anybody who's even looked at skin shading in a small way that skin is translucent and it behaves similarly to how things like wax or slightly translucent plastic do. Things like jelly or even some types of glass, they have subsurface scattering in them, which means that the light enters and then exits with a different color. So the light coming from this light right here is pretty close to white, and when it enters the surface of the skin shader, it goes in and then exits again with a different color, depending upon how far into the model it goes. So this is subsurface scattering. It goes in, scatters around a bit, and then comes out. Now this is very similar to how I described basic albedo or diffuse as working, except in that case it's such a small scale interaction with the surface that using a subsurface scattering map wouldn't really make sense in most cases. For example, if you have spray paint applied to a surface, the light is going to go in sub-millimeter depths and then shoot right back out. But if you have skin, it might not just enter and exit, but it might actually go through. For example, with his ears, let me turn this off, turn that up. With this guy's ears, you might actually see that the light pushes all the way through and exits on the other side. Now, this has an interesting effect. The fact that the light enters and then exits in a different place means that the light on this side is going to have a different color. So some of the light certainly will hit and then shoot right back towards your eyeball or the camera, but since some of it is going through and taking on this color, or some of it is just being absorbed, it means that the color coming back to your eyes is going to be modified according to whatever this transmission color is. So the color that comes out, depending upon the viewing angle, is going to be different. So the more it's facing away from the camera, the redder it's going to be, and the more it's facing towards the camera, the cooler it's going to be in general. So let's turn that down a little bit. So if I have a very high scatter depth on here, let's just turn that off, and I set this to a bright red color. Often what you'll see, especially in areas like this, is that you get bright red, sure, but you also get this kind of greenish halo around that. Now this is happening because there is light going in and then coming out over here, but not as much is coming out over here, and the light that's coming out over here is looking less red because most of the red light is coming out over here. Now this is a component of energy conservation. Any light that goes in, no matter what the color, if it exits, it has to respect how much of one color of light is coming out, no matter what part is actually being reflected and where it's being reflected. So the more reddish or orangey the subsurface scattering color is, the more you're going to find that a lot of other highlight areas start to look very cool in comparison. This is not actually an error, this is a physical property of how light works, and a physical property of how translucent materials work. And now, granted, this is not something you will see in everyday life simply because you don't generally run into surfaces that reflect light in quite this way. However, if you go looking for it, you can actually find very similar behavior in the real world. So if you ever run into situations where a nice subsurface scattering color that you think is going to look right ends up looking bizarre, this is probably why it's happening. So you can see similar behavior happening with different subsurface scattering colors. As I change this to, say, a cyan color, the translucency along these edges starts to look more cyan. However, stuff that's right next to it takes on a warmer cast simply because there is less cyan bouncing out back in this direction. So let's take a look at some refraction. Refraction is always fun, and it's something that is pretty difficult to achieve, and pretty difficult to achieve in a way that looks realistic. Now, in the past, programs like, well, actually Marmoset Toolbag actually didn't have a refraction shader for quite a long time because they're hard to program and they're hard to get working with the many different layers that go into a shader, and I'll explain why in just a second. So let's do some quick refraction on this guy to take a look at how refraction works, how it obeys things like conservation of energy, and how you can use things like gloss and specular to achieve some fun results. Now, this is going to be pretty useful if you're working on characters that say are supposed to have glass on them or gemstones. And there are some important considerations to take to keep in mind if you're doing things that involve things like gemstones. So let's try that now. Let's change the, oh my, let's change the transparency to refraction and take a look at how this looks. Okay. So, interesting, kind of cool. However, you're probably noticing that there's some odd stuff going on. Namely, when I look right here, I would expect to see the eyeballs being refracted around his eyes instead of them being refracted way over here or down there. Now, part of the reason that this happens is because the index of refraction is too high or too low. So if I take the index of refraction and I push it down, 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 you're going to start to see that his eyeballs are not refracting way out through the rest of his head, but are actually a little closer to where you'd expect. Now, what does index of refraction actually mean? Well, let me just pull out one of my notes, 1 second. Okay, so the index of refraction represents a few things, but in general, what it means is that the material that light is passing through will refract light in some given manner. So an index of refraction that is, say, 1 will have light going essentially straight through it. Let's turn the gloss way up so this just looks like glass. Okay. Actually, let's turn that to 0. Okay. So a material that has an index of refraction, and actually basically all materials have indices of refraction, not necessarily because all of them seem to be very refractive, but more because of how I've mentioned that light passes through materials and then exits again. Now, things like paint or wood or skin or glass or any number of other everyday materials, they're going to have an index of refraction. However, that's going to be strongly modified by how much light they're actually able to refract and reflect, simply because of the way that the molecules and such are arranged. This is not something terribly important for a character artist to know, but it's important to have a good basic understanding of what index of refraction is. A physical property of most materials is they have an index of refraction. However, the only time you're ever going to really use it when you're doing character art is for items like glass, gemstones, and the like. Index of refraction says that the higher the number, the more it's going to bend light as it goes through it. So light will pass in at one angle and exit at a completely different angle, meaning that the light being reflected off these eyes is naturally going to have a different position than it would if this was simply like a ghost or a little bit of smoke. You'll notice that, for example, dithered transparency, if I turn this down, doesn't change the way that these eyes are displayed, because it doesn't take into account index of refraction. It just draws the polygons on top of one another without taking into account any sort of refraction or distortion. But back to refraction. So, refraction in general is a screen space effect. So what does this mean for us? Screen space effects are effects that are based on what is actually being drawn on your screen, your TV, your computer monitor. And what they do is they take the image and they transform it or alter it in such a way that it's modified to fit some idea of how a material should behave or an object should behave. Let's take a look at another example of a screen space effect to get a better idea of what we're talking about. If I go into the camera settings here, I can apply a screen space effect to the entire screen in the form of distortion. Here I'm applying barrel distortion to the scene. This is a screen space effect that basically says I want all of the pixels in the middle of the screen to look like they're bulging outwards. Now, if this was an effect based on a physical camera, you would end up seeing a lot more of the scene outside of here if there were other props and such. But in this case, all it's doing is sampling whatever is on the screen and transforming it somehow. Now, by that same token, I can change things like chromatic aberration to make it so that let's really crank this up, so that the different color channels are displayed offset from one another. So here I am offsetting the red channel of what's being rendered so that it looks like the chromatic aberration effect that's present with bright lights and cheap camera lenses. It's a simulation of effect, but it often, transforming the color channels by just making them larger or smaller on the screen has the effect of simulating that real world effect. Now, back to refraction. Since refraction is a screen space effect, there are some things that it's not capable of doing very well or very accurately. Now you notice that if we zoom in here, you would expect that you'd be able to see more of the eye, no matter what the index of refraction, simply because there's an eye behind there. You'd expect to be able to see some of that eye if this was a real-world translucent material, and then, around here there would be more stuff. So since this is a screen space effect, what it's doing is it's taking the normals of the world space normals of this object and transforming whatever it sees on screen according to those normals and a bunch of math that goes into it, and reprojecting it onto the screen, and the intensity with which it transforms according to the normals of the object depends entirely on the number that we put into this little slider. So there are some cool things that you can do with modern transparency and translucency. For example, you can have a different index of refraction, sure. So that's going to, here, let's pull up his hair. And we can actually refract the inside of his hair in an interesting way. Or let's change the color of the glass. Ooh. Well, this is interesting. So what's happening here? Well, once again, this is an example of conservation of energy. Now, let me change the sky to here. And you'll notice that if I have just the color, a flat color in the sky, we're not actually getting anything coming through here. All we're seeing is a little bit of the eyes in there. Now, this is one example of a limitation of screen space effects. It doesn't take into account just the color that we have plugged into here. It could be for any number of reasons. However, if we turn the sky on, now you can see that it's refracting the sky. Once again, that could be an oversight in the way that the shader was written. It could be a technical reason behind how the color is displayed. But once again, that's an example of how limited screen space effects can be. Now, if we duplicate this guy and move him like this, and then if we duplicate this shader and give it a different tint color, and just plop it onto there, we're going to start seeing some other interesting effects. For example, we're going to see effects of energy conservation. Here you can see that with a green transparency color, if you overlay one on top of the other, you don't see a lot of light coming through. This is because when light is coming through this green shader right here, not a lot of red light is coming through. Conversely, not a lot of green or blue light is coming through this model. So if you start rendering one on top of the other, barely any light is coming through because there's very little red light to come through this model. Omar asks, if this works with a blurred sky. Well, let's take a look. I mean, this could just be a limitation of the way that Marmoset handles their rendering, but we can take a look. And this is an example of an effect that, depending upon the engine that you're using, may work in different ways. But let's take a look in Marmoset just to see what it shows. So yeah, it looks like it does take into account the blurring of the backdrop. However, keep in mind, if you're using something like Unreal 4, the way that it's going to render this this effect is that it simply won't it won't be the same. There will be other technical challenges involved in it. But I have an idea. Let's go back to here, change this backdrop color to bright pink. Go back to color. Let's change this. Oh, well, looks like I was wrong. I was wrong about something interesting, and I didn't even account for it. So, as I mentioned before, when I was talking about how they refract through each other, if the backdrop is it only has, or if the model has just green light coming through it, or only red light coming through it, and not a lot of red light is coming through this one, or vice versa from this angle, you're going to essentially just get black translucency because barely any light comes through. However, if you change the backdrop color to something, say, white, you're going to get some more of the correct colors coming through. Well, cool. So that's an interesting example of how refraction can behave. However, there's also some other interesting things that refraction can do. For example, if you had a sphere of glass, some sort of colored or simply clear translucent glass, and the surface of it had a texture to it, say it had been sanded, something that many modern translucency and refraction shaders will take into account is the fact that when light scatters through frosted glass or glass that has a very, very fine texture on it, it will blur out what's behind it. So let's turn the background back on to get a better idea of how that works. Change that back to sky. Okay. And we'll change this to a different preset that's a little bit better for our purposes. Let's just change it to, oh, what's a good one? Here we go. This is a good one. Has lots of contrast in it. So you'll notice when looking through this red head that as I turn up or lower the gloss, it actually starts to look more and more like frosted glass. It blurs what's behind it, and it also blurs the reflections, the specular reflections, a corresponding amount. Now, once again, this is a screen space effect that has some limitations to it, and you know, can occasionally be kind of buggy just because of how this multi-pass rendering works, this layered rendering works. Sometimes, depending upon the index of refraction that you're using, or the colors you're using, or even the number of translucent objects that you have in the scene, sometimes you won't actually be able to get what you want out of what you're seeing, simply because you have two translucent things that are based on world space, or screen space effects. And this is partially why, when we're trying to render these two translucent objects in front of each other, we don't always get the effects that we're looking for. Sometimes things start to just disappear, or or if you have two objects that, or if you have one object that has overlapping pieces. For example, let's change the background again so that we can see this a little better. Something that has less contrast in certain areas. You'll notice that, for example, this ear right here doesn't double up the refraction with the back of the head, so the amount of refraction that you see is not quite what you would see on a real object, because even though it has multiple layers and multiple different refractions going on, it can't actually render what's behind the ear as a separate pass. So it does have limitations. There are, it's not perfect, but it's still a really fun, cool effect. Okay, so there are some limitations to what I've been talking about. There's a lot of other stuff to go over, and I'm sorry that I wasn't able to do more in Unreal. In future editions of this workshop, I'll try to get that situation sorted out. But for now, I think I'm going to leave it there. That's a general overview of shaders, how shaders can affect the shading on a character, the light behavior on a character. It's sort of a basic overview of the different types of shaders that you will see on characters, and sort of a basic overview of what a shader is and how it affects what you do. It's only 8:30-ish, so there's still half an hour left for there's still half an hour until the time I had originally planned to cut off the stream. So if there are any questions from anybody who's watching, feel free to ask. I'm going to be on for maybe the next 5 to 10 minutes, depending upon how many questions there are. And since I'm more or less done talking about what I had in mind, I'm going to then cut it off and go into the private hangout with the program members. So does anybody who's watching the Twitch channel have any questions or comments or anything that they'd like to know that's sort of within the scope of what we've been talking about tonight? So one question is, besides translucency, are there any other maps that are particular to skin or have to be made differently for skin than other materials? That's a very good question. So skin is, as you probably gathered, skin is a pretty big topic for people who, work on characters and that type of thing. And clearly, you're going to need some sort of texture to control how the translucency or subsurface scattering of the skin behaves. As far as creating textures that are specific to skin, that aside from translucency and that type of thing, in general, there are not too many specific textures that need to be made only for skin. However, sometimes that's not the case. For example, if you want to have good skin shading, and most of your characters are going to be in more or less top-down lighting, sometimes what you'll want to do is render out an ambient occlusion map to plug into the shader which can affect how the shading works under different lighting circumstances, especially if you want it to look like there is uh, only light coming from above in, say, a dome. So if most of your characters are, say, walking around a city, you might actually want to bake directional ambient occlusion into your textures, or a separate directional ambient occlusion map, so that in the lighting conditions that most of your characters are going to be seen in anyway, uh, they will the skin shader will have a lot more information than it would get from screen space ambient occlusion. So in that case, what you would do is basically just render out an ambient occlusion map with a plane underneath your character, and that'll block any rays coming from down below. So things like the bottom of the jaw, the bottom of the nose, areas under the eye right here, or the brow right here and such, they'll get a lot less light than, say, the top of the head, the top of the nose, the top of the lower lip, that type of thing. Occasionally, you'll want to author maps that define different colors for the the subsurface scattering. For example, on this character, I might want to have a cooler or a yellowish color for the subsurface scattering on his forehead, and maybe a warmer color for the tip of the nose. It can be sort of a stylistic choice. However, if you look at a real person, you might notice that a lot of the time the light coming through, say, their ear when they're backlit ends up being not just reddish, but also orange or yellow, depending upon how thin it is and whether there are any veins present. So that is, getting the right color for that. That may be a map that you would render or paint, but once again, that's a very sort of edge case type of texture, where you might only use it for, say, a hero character or something, sometimes even for a specific shot. Something else that you'll often have is tiling skin texture for just little tiny micro details that you wouldn't even see from this far away, but maybe if it's a tight close-up, you'd see just a tiny bit of gloss breakup. But once again, depending upon the limitations of your shader system or your rendering, you might not even be able to have something like that. So then there's another question. How often are displacement maps used on characters, or is that mostly for environment artist set pieces like the one on my VV model? That's a good question, and it really depends on sort of what you're looking at and what you're looking for in a character. Some large set piece characters, like say you were doing a boss battle for something that has huge bosses, like a Dark Souls game or something, those might be situations where you would have displacement maps. However, the math and the shading involved in getting displacement maps working properly without any problems, it can be kind of tough. There are a lot of limitations to using displacement maps in games, with at least with current shader technology. So sometimes you'll get things like tearing at UV seams because the shader doesn't know how to smooth out the positions of two different UV islands based on the levels in the displacement map. So occasionally you'll get things like Z-fighting or simply like tearing in the model, where little bits are just coming apart and you can see through. But other times you'll actually get models that have full displacement detail on them, simply because it's faster and cheaper to do that than to model certain things out, especially in games like, say, The Order, where you have transformations between different models. Even though they did most of that with blend shapes and other similar rigging tricks, that's an example of where you could have a displacement map, since most of that occurred in cutscenes anyway, which are very controlled circumstances, and that's where you could usually pretty safely use displacement maps. Yeah, sometimes you'll use parallax for things like that. For example, it's a pretty common trick to use parallax for things like eyes, like I had mentioned before. These eyes just use parallax mapping, and this is a trick that gets used in lots and lots of different games. It's something we've used at Insomniac. It's something that you'll see in a lot of different places. Even though the uh, the parallax shader can be kind of expensive, because it's a fairly small effect on the screen. Oftentimes, the computer only has to process a few pixels, so it ends up being cheaper and easier than having to model something out and then have a refraction shader and all kinds of other stuff. Are there any other questions that you guys have? If there are not, I'm just going to end up shutting down the stream for tonight, and then going into the private hangout session for a bit with the program members. All right. So since it doesn't seem like there are any more questions at the moment, I'm going to be shutting down the stream in just a sec here. Hope you enjoyed this. I'm sorry for the technical difficulties and stuff, and I know that it kind of threw me off a little bit, so I had to kind of blast through some things, and I might have been stumbling on my words on occasion. So yeah, once again, sorry for that. I'll try to get any potential problems sorted out before the next stream. In the next stream, I'm going to be taking a bit of a step back and talking about UVs, a little bit about baking, and how you can use things like tiling textures, how you can orient your UVs in ways that are really good for characters and character modeling, along with character texturing. I'm going to touch on things like using cloth shading and tiling detail maps for nice, tight, crunchy detail. And I'm also going to be talking about just a little bit about baking and some of the considerations that you need to make for baking current generation high-end characters. And finally, I'll be talking about the different problems you might run into when baking using, say, overlapping or offset UVs, and how you can sort of work effectively within the 0 to 1 or outside the 0 to 1 UV space. So it's going to be a little bit of a more technical jump in than these previous ones where I've mostly been talking about the art aspects, but it's something that's pretty important to consider when you're doing your character modeling. Additionally, I'm going to be talking about how you can optimize your UV seams and make sure that you have either the correct seam placement or better UV island arrangement and unwrapping, just to show how things can be affected by different UV island placement and shapes and that type of thing for baking purposes and final rendering purposes. So I hope you guys enjoyed tonight's stream. I hope you'll tune in for the next one. And if you have any questions or anything to comment on, I'm always on Twitter and all kinds of other social media places. So just, look me up. I have links down below the stream. And hope you had a good night. Thanks again for watching. And I'm going to shut the stream down now and go to the private chat.